NASA just confirmed, we're living inside a false universe. NASA just released data that contradicts everything we thought we knew about reality. And they buried it in technical papers most people will never read. For 70 years, we believed the universe stretched infinitely in all directions. Equal density everywhere. Same laws of physics from here to the edge of observable space. That assumption just collapsed. Because in 2013, 3 scientists discovered something that should not exist. We are sitting inside a void. A cosmic bubble so massive it spans 2 billion light-years. And the strangest part? The universe expands differently here than it does everywhere else. This is not speculation. The measurements have been verified by multiple independent teams. The data is public. Yet somehow this discovery stayed hidden in academic journals while the world kept believing we understood our place in the cosmos. We did not. We still do not. Because if we are inside this void, then every measurement we have ever made about the universe's age, its expansion rate, its ultimate fate, all of it might be wrong. Right now, space itself is lying to us. Stretching faster around our position than the equations predict. Creating an illusion that fooled astronomers for decades. The numbers say one thing. Reality says another. And NASA finally admitted they cannot explain why. What you are about to hear will change how you see the night sky. Because that darkness between stars? It goes deeper than anyone imagined. We are not exploring the universe. We are trapped inside a distortion. And the walls of this prison extend farther than light can travel in 2 billion years. This is the story of how scientists discovered we live inside a cosmic lie. How the void warps measurements of time itself. And what it means that humanity developed consciousness in the emptiest region of observable space. The discovery started with a simple count. 3 astronomers wanted to map galaxy distribution across deep space. Standard survey work. Nothing revolutionary. Ryan Keenan, Amy Barger, and Lennox Cowie pointed their telescopes outward and began cataloging everything they could see. 35,000 galaxies. Positions recorded. Distances calculated. Densities measured. Then the numbers stopped making sense. Every direction they looked, the galaxy count came up short. Not by a small margin. 20% fewer galaxies than there should be. The deficit stretched outward in every direction for 1 billion light-years. Perfect sphere. Us near the center. At first they assumed measurement error. Checked the equipment. Reran the calculations. Used different galaxy surveys to cross-reference the data. Same result every time. The region around Earth contains significantly less matter than the cosmic average. Not slightly less. Dramatically less. An underdense bubble on a scale that challenges the fundamental assumption of cosmology. That assumption is called the cosmological principle. It states the universe is homogeneous. Same density everywhere once you average over large enough volumes. Same structure. Same properties. No special locations. That principle forms the foundation of every model describing cosmic evolution. Without it, the equations break down. Predictions fail. The entire theoretical framework collapses. This void violates that principle. Because according to computer simulations, a region this large and this empty should be extraordinarily rare. Less than 1 in 1,000 universes would randomly produce such a structure. Some calculations put the odds even lower. 10 sigma deviation from average density. Statistical language for something so improbable you might search the entire observable universe and never find one. Yet we live inside it. The void earned a name. KBC Void. Using the initials of its discoverers. Sounds almost casual. Like naming a crater on Mars. But this is not a crater. This is a fundamental challenge to everything cosmology claims to understand. Because if our location is this unusual, then every measurement we make is potentially biased. When telescopes point at distant supernovae to calculate how fast space expands, are they seeing true cosmic expansion? Or a distorted local version influenced by the void's peculiar physics? That question led to the second revelation. One that made the void impossible to ignore. Astronomers had been fighting over a number for years. The Hubble constant. Measures how fast the universe expands. Different methods gave different answers. Ancient light from the early universe suggested one value. Nearby supernovae suggested another. The discrepancy was 9%. Sounds small. Means everything. Because both measurements are incredibly precise. Both should give identical results if our understanding of physics is correct. They do not. The mismatch reached 5 sigma statistical significance. 1 in a million chance it is random variation. Scientists call this the Hubble tension. Crisis-level problem in modern cosmology. Suggests either our measurements are systematically wrong or the theoretical models predicting expansion need revision. Neither option is acceptable. The measurements have been checked repeatedly. The models have been tested across multiple contexts and consistently work. Then someone calculated what the void would do to local measurements. If Earth sits inside a massive underdense region, gravity from denser matter outside the void pulls galaxies within it outward, adding extra velocity to their recession, making the local expansion appear faster than average. That extra velocity would inflate the Hubble constant measured from inside the void. The prediction matched observations exactly. Suddenly the conflicting measurements made sense. We are not measuring the universe's true expansion rate. We are measuring the expansion rate plus the void's outflow velocity. The cosmic microwave background measurement probes the early universe before voids formed. That gives the accurate global value. The supernova measurement probes our local region. That gives the distorted value. The void explains the Hubble tension. But accepting that explanation requires accepting something uncomfortable. Our location is special, unusual, not representative of the universe as a whole. Every headline about accelerating expansion and dark energy dominating the cosmos might be describing a local phenomenon, not a universal truth. That realization sent shockwaves through the scientific community. Because it violates the Copernican principle. The idea that Earth occupies no privileged position. History spent 5 centuries removing humanity from the center of anything. Earth is not the center of the solar system. The solar system is not the center of the galaxy. The galaxy is not the center of the universe. And now we are supposed to believe we randomly ended up inside one of the largest voids ever observed? A structure so rare that simulations struggle to produce anything similar? The statistical improbability bothers everyone. But the evidence keeps accumulating. And it gets stranger the deeper you look. Cosmic voids are not truly empty, which makes them even more disturbing than their name suggests. When astronomers say a region is a void, they mean it contains far less matter than average. Not zero matter. Just dramatically less. The KBC void has roughly 15% of normal cosmic density. Picture space where instead of 10 galaxies in a given volume, you find 1 or 2. Scattered islands in an ocean of near nothingness. Between those rare galaxies stretches space containing mainly dark matter, dark energy, and occasional clouds of hydrogen gas too diffuse to form stars. The density is so low that gravity barely functions. Without enough mass to pull things together, structure formation stalls. No new galaxy clusters can emerge. No rich superclusters develop. The void stays empty. This has consequences that ripple through physics itself. Gravity is already the weakest fundamental force. Requires enormous masses like planets to show noticeable effects. In a void where mass is scarce, gravity becomes essentially irrelevant. The dominant force becomes dark energy, the mysterious component accelerating cosmic expansion. In dense regions packed with galaxies, gravity fights against dark energy, slowing expansion in those areas. Inside voids, gravity loses that battle decisively. Dark energy wins. Result: voids expand faster than the rest of the universe. They grow like bubbles, pushing boundaries outward while filaments of galaxies around them act as walls. This creates a feedback loop. The more a void expands, the emptier it becomes, which allows even faster expansion. Scientists measured this effect directly. Galaxies near void edges move outward faster than cosmic expansion alone predicts. Something is pushing them. That something is gravitational pull from matter outside the void. Think of a void as a valley surrounded by mountains. Gravity pulls downhill from mountains toward the valley. But because we are discussing space rather than terrain, That pull makes galaxies fall outward, not inward. The effect is measurable. Our own galaxy is moving away from the local void at 600,000 miles per hour, driven by gravitational imbalance. The interior of a void becomes a strange place for physics. Light travels through it experiencing less gravitational influence than light passing through normal space. This affects observations in subtle ways. When astronomers study cosmic microwave background radiation, the faint afterglow from the Big Bang, they notice light passing through voids appears slightly cooler. Reduced gravity causes less gravitational redshift. Shows up as cold spots in temperature maps of the early universe. These cold spots align perfectly with where large voids exist today. Not coincidence. Physics. Understanding what makes voids empty helps explain why they matter for cosmology. They are not boring blank spaces between interesting structures. They are laboratories where dark energy dominates, where gravity takes a backseat. By studying how matter behaves differently in voids versus dense regions, scientists test fundamental theories about how the universe works. The KBC void might be unsettling because it makes us question cosmic typicality. But it offers a rare opportunity. We are positioned exactly right to study the universe's most extreme low-density environments up close. Except the structure containing these voids is more disturbing than anyone imagined. The universe resembles Swiss cheese. Dense matter forms walls and filaments surrounding enormous hollow pockets. This architecture is called the cosmic web. Largest structure in nature. Galaxy clusters concentrate where multiple filaments intersect, creating nodes of intense matter density. Stretching between them run filaments. Long chains of galaxy groups extending hundreds of millions of light-years. These form walls. Vast sheets where galaxies gather in higher concentrations. Between walls and filaments lie voids, taking up most of the volume while containing almost no mass. This structure was not always obvious. For decades astronomers photographed the sky and counted galaxies. But three-dimensional arrangement remained hidden. Only when scientists began measuring galaxy redshifts in the 1970s and 80s did the cosmic web reveal itself. Redshift surveys let them calculate distances by measuring how much expansion stretched light toward redder wavelengths. Suddenly distribution snapped into focus. Universe had structure on scales nobody expected. First major void discovery came in 1978. Two independent teams identified large underdense regions. More surveys followed, each mapping deeper into space, revealing increasingly intricate webwork. Sloan Digital Sky Survey began in 2000 created spectacular three-dimensional maps spanning billions of light-years. Maps show the cosmic web in stunning detail. Filaments twist and branch like blood vessels. Voids appear as dark bubbles, sometimes 500 million light-years across. Largest structures include the Sloan Great Wall, a filament nearly 1.5 billion light-years long. On opposite end, supervoids like the Eridanus void stretch 1.8 billion light-years wide, even emptier than KBC void. Together these features paint a picture of a universe organized on scales far larger than predicted. Galaxies are not fundamental building blocks. The web itself is the structure. Galaxies just mark where matter happens to concentrate. Why does the universe organize this way? The answer reaches back to the beginning. Immediately after Big Bang, matter was not perfectly uniform. Quantum fluctuations during the universe's first fraction of a second created tiny variations in density. Some regions slightly denser than average, others slightly less dense. Differences were minuscule, maybe 1 part in 100,000. But gravity amplifies even tiny advantages. Denser regions pulled in more matter, making them denser still. Less dense regions lost matter to surroundings, becoming emptier. Over hundreds of millions of years this process snowballed. Small clumps merged into larger clumps, which merged into galaxy clusters, which aligned into filaments. Meanwhile underdense regions expanded into voids. Cosmic web is essentially gravity doing its work over cosmic time, turning barely noticeable initial ripples into grandest architecture in existence. Today voids occupy roughly 90% of space's volume. Filaments and clusters make up remaining 10% but contain most mass. This imbalance defines the universe's character. We live not in a cosmos filled with galaxies but in a cosmos of emptiness punctuated by occasional matter concentrations. KBC void is just one bubble in this foam. But it is our bubble. And that makes all the difference for what we observe and how we interpret the universe. Here is what makes this truly disturbing. Milky Way is not at the void center but close enough to matter. Measurements place our galaxy somewhere between 200 and 400 million light-years from the void's actual center. Sounds like huge distance. It is compared to anything humans experience. But the void extends outward for a billion light-years in every direction from center, making our offset relatively small. We sit well within the underdense region, surrounded by low-density environment in all directions. This position has consequences for every observation we make, every conclusion we draw about cosmology. If we were located outside the void entirely, in one of the dense filaments, our measurements would look completely different. We would calculate a slower expansion rate. Hubble tension would not exist. Our larger cosmic neighborhood adds another layer. Milky Way belongs to the local group, collection of about 80 galaxies including giant neighbor Andromeda. Local group sits within Laniakea supercluster. Massive structure containing roughly 100,000 galaxies spread across 520 million light-years. Laniakea is enormous by any standard. Yet even this supercluster resides within KBC void. Think about that. A structure containing 100,000 galaxies still counts as part of an underdense region. The void is so vast it can swallow entire superclusters and still have room to spare. Local group is also influenced by another nearby void called local void, distinct from but connected to larger KBC void. Local void extends about 200 million light-years. Sits adjacent to our position. Our galaxy is rushing away from it at 600,000 miles per hour, pushed by gravitational pull from denser regions beyond. This motion is separate from cosmic expansion. It is peculiar velocity. Results from local gravitational effects rather than space stretching. These peculiar velocities complicate efforts to measure true expansion rate because they add extra motion on top of expansion signal. Inside a supervoid, those effects are amplified and harder to separate cleanly. Void's influence reaches farther. When scientists measure galaxy motion out to distances of 250 million light-years, they find bulk flows exceeding predictions from standard cosmology. Entire regions moving faster than they should, flowing in coherent patterns driven by void's gravitational imbalance. KBC void creates large-scale velocity field affecting everything within it. Galaxies are not passively expanding with the universe. They are actively responding to gravitational landscape, accelerating outward from underdensity toward denser structures beyond void's edge. Our position inside the void affects what we can see. Light from distant galaxies travels through the void on its way to our telescopes. That light experiences less gravitational interaction than light traveling through denser regions. Reduced gravity creates subtle effects on the light's wavelength and energy. Additionally, the void influences matter distribution we observe. When we look outward from inside the void, we see the shell of denser material surrounding us in all directions. That shell appears as concentration of galaxy clusters and filaments at specific distance range. Beyond the shell, universe returns to more typical density. This creates observational bias. We are not sampling random location in universe. We are sampling from inside one of its most extreme features. Living in the void means living with systematic uncertainty about how typical our measurements really are. And that is where the real problem begins. Every measurement about universe expansion rate might be wrong. Not because scientists made mistakes. Because we are measuring from inside a cosmic hole that distorts the signal. Problem reveals itself when astronomers use different methods to calculate Hubble constant. The number telling us how fast space expands. One method looks at cosmic microwave background. Ancient light from when universe was 380,000 years old. This light encodes information about early universe density and expansion rate. Scientists feed data into cosmological models and calculate what expansion rate should be today. Answer comes out to about 67 kilometers per second per megaparsec. That means for every megaparsec of distance, roughly 3.3 million light-years, Space expands at 67 kilometers per second. Second method looks at nearby objects with known brightness, specifically Type Ia supernovae and Cepheid variable stars. These serve as cosmic measuring sticks because astronomers understand exactly how bright they should be. By comparing actual brightness to apparent brightness as seen from Earth, scientists calculate distance. Combining distance measurements with redshift measurements gives expansion rate directly. This local method consistently produces higher number, about 73 kilometers per second per megaparsec. Difference is 9%. Both measurements incredibly precise with very small error margins. Both should give same answer if cosmology is correct. They do not. This discrepancy is Hubble tension. Has reached 5 sigma statistical significance. Less than 1 in a million chance it is random variation. KBC Void explains why these numbers disagree. When we measure expansion rate using nearby supernovae, we are measuring within the void. Void's low density means less gravity pulling back on expansion. Matter from denser regions outside the void gravitationally attracts galaxies within it, adding extra outward velocity. Galaxies appear to recede faster than they would in typical region. This inflates local Hubble constant measurement. We are not measuring universe's true expansion rate. We are measuring expansion rate plus void's peculiar velocity field. Effect is large enough to account for most or all observed tension. When scientists model how a void of KBC's size and depth would affect local measurements, they find it could boost apparent expansion rate by exactly the amount needed to match observations. But here is where it gets uncomfortable. If void explains our local measurements, then those measurements do not tell us about universe as a whole. They tell us about our weird local environment. Cosmic microwave background method is unaffected by void because it probes early universe long before voids formed. That measurement might be accurate one for universe's global properties. This means most headlines about accelerating universe and dark energy might be describing local phenomenon rather than universal truth. We spent decades building cosmological models based partly on local expansion measurements. And those measurements might be systematically biased by our location. Some scientists resist this conclusion because it violates cosmological principle, the assumption that Earth does not occupy special location. Finding ourselves inside supervoid that significantly affects measurements seems to contradict that idea. Suggests we are in unusual location. Makes physicists uncomfortable. Science progressively decentered humanity from special cosmic positions. Earth is not center of solar system. Solar system is not center of galaxy. Galaxy is not center of anything. And now we are supposed to believe we happen to live inside one of largest voids ever observed? Statistical improbability bothers many researchers. Yet evidence keeps mounting. Void exists. Our measurements are discrepant. Void's effects match observations. Whether we like implications or not, universe might actually be lying to us about expansion rate. Or more precisely, our location causes us to misinterpret what we measure. Crisis this creates in cosmology runs deeper than most realize. Hubble tension is not just inconvenient disagreement between two measurements. It represents fundamental challenge to understanding of cosmic evolution. Cosmology rests on framework called lambda cold dark matter, the standard model of cosmology. This model has been spectacularly successful at explaining observations from multiple sources. Accounts for cosmic microwave background temperature fluctuations, abundance of light elements like hydrogen and helium, formation of galaxies, large-scale structure of universe. For decades it has been consensus model because it works so well in so many contexts. But Hubble tension suggests something is missing or wrong in this framework. When a model's predictions disagree with observations at 5 sigma level, scientists must take that seriously. Tension matters because expansion rate determines everything else about cosmic history. If universe expands faster, it reaches current size in less time, making universe younger. Current calculations based on cosmic microwave background put universe's age at 13.8 billion years. But if higher local measurement is correct globally, universe might be only 12.7 billion years old. That creates immediate problems. We observe stars in globular clusters appearing to be 13 billion years old based on stellar evolution models. These stars would be older than universe itself, which is impossible. Either our age measurements for stars are wrong, understanding of stellar physics is wrong, or higher Hubble constant does not apply to early universe. None of these options are comfortable. Tension also affects understanding of dark energy, mysterious force accelerating cosmic expansion. Dark energy makes up about 68% of universe's total energy content according to standard models. But its properties depend sensitively on expansion rate. If expansion rate is higher than we thought, dark energy's behavior might differ from current models assume. Some researchers propose dark energy evolves over time rather than being constant. Revolutionary if true. Others suggest we need to add new physics to early universe. Perhaps extra burst of accelerated expansion shortly after Big Bang. Every proposed solution introduces new complications. Requires evidence beyond just fixing Hubble tension. Dozens of alternative explanations have been put forward. Some scientists propose measurements themselves contain subtle systematic errors overlooked. Perhaps dust between galaxies dims supernovae more than accounted for, making them appear farther away. Inflating expansion rate. Or maybe Cepheid variable stars behave differently in different environments, biasing their use as distance indicators. These explanations keep getting tested and ruled out as measurement techniques improve. Measurements are solid. Other researchers suggest modifications to general relativity. Einstein's theory of gravity. Maybe gravity works slightly differently on cosmological scales than we think. Would change predictions for expansion. This route leads into controversial territory because general relativity passed every other test thrown at it. Void hypothesis offers cleaner solution requiring less modification to fundamental physics. Simply states we are in unusual location and local measurements reflect that, rather than reflecting universal properties. This explanation bothers people philosophically but requires fewer assumptions than inventing new particles or changing gravity. Recent work strengthened void hypothesis by showing it naturally predicts other observations. For example, outflow velocity from void should affect not just expansion rate but also motion of galaxy clusters in our vicinity. Measurements of these bulk flows match void predictions. Hypothesis is making testable predictions being confirmed. Nevertheless, debate continues. Not all cosmologists accept void explanation. Some argue even a void as large as KBC cannot produce big enough effect to fully explain tension. Others point out supervoids this large should be rare. Finding ourselves in one just when we develop precision to measure Hubble constant seems suspicious. Maybe we are interpreting data incorrectly somehow. Controversy remains unresolved. Why Hubble tension continues to be called crisis? Not just a number that is off. Signal that understanding of cosmos might be incomplete. And the deeper you look, the stranger it gets. Gravity inside a void does something counterintuitive. It pushes outward instead of pulling inward. Not because gravity itself reverses. Force of gravity always attracts mass toward mass. But geometry matters. Imagine standing in shallow valley surrounded by mountains. Gravity pulls you toward mountains, which means pulling away from valley center. Inside cosmic void galaxies experience same effect. All matter lies outside void in surrounding filaments and clusters. That exterior matter gravitationally attracts interior material, pulling galaxies outward from void center toward denser regions beyond. Result is outflow. Systematic pattern of galaxies accelerating away from underdense region. This outflow is measurable and significant. Astronomers track galaxy velocities using redshift measurements combined with distance estimates. When they map velocities around known voids, pattern is clear. Galaxies near void centers moving faster outward than cosmic expansion alone predicts. Effect strongest near void center. Weakens toward edges where matter density increases. For KBC void specifically, outflow adds hundreds of kilometers per second to galaxy velocities within void. Our own galaxy participates in this pattern. Milky Way moving at 600,000 miles per hour away from nearby local void, driven by gravitational imbalance. This motion combines with other local effects like gravitational pull from Virgo cluster to create our galaxy's overall peculiar velocity. Outflow has implications for cosmic expansion measurements. When we observe distant galaxies and measure redshift, we are seeing combination of two effects: expansion of space itself, and peculiar motion of galaxies due to gravity. Normally scientists can separate these components because peculiar velocities average out when you look at large enough volumes. For every galaxy moving toward you due to local gravity, another moving away. Average is zero. But inside void, peculiar velocities do not average out. They all point same direction, outward. This creates systematic bias, inflating apparent expansion rate when measured from within void. Problem compounds at different distance scales. Close to void center, outflow is rapid. Farther from center but still within void, outflow is slower. Beyond void's edge, peculiar velocities might even reverse as matter falls back toward denser filaments. Creates complicated velocity profile varying with distance. When astronomers measure Hubble constant using supernovae at different distances, they are sampling this varying velocity field. If most supernovae lie within void, which they do because we deliberately avoid using extremely distant supernovae due to other complications, measurement gets boosted by outflow. Further out you measure, less void effects result. This predicts Hubble constant should appear to decrease with distance. Recent observations confirm exactly that trend. Modeling these effects requires careful calculation. Scientists must estimate void size, depth, density profile. Then calculate gravitational potential it creates. That potential determines how fast material flows outward at each radius. Calculations show void roughly 1 billion light-years in radius with 20% density deficit can easily produce observed velocity anomalies. Match between predictions and observations is good enough that many researchers find void explanation compelling. However, standard cosmological model struggles to explain how such large void formed in first place. Computer simulations based on lambda cold dark matter rarely produce voids this extreme. When they do, requires very specific initial conditions statistically unlikely. This raises troubling possibility. Maybe our cosmological model is missing something. If voids larger and deeper than expected keep showing up in observations, perhaps structure formation works differently than standard theory predicts. Some scientists propose modified gravity theories where gravity is stronger on large scales. Would enhance structure formation. Make big voids more common. Others suggest universe is simply more inhomogeneous than assumed. Would also make large voids less surprising. Either way, backwards gravity in voids tells us something important about cosmic evolution. And our motion through this gravitational landscape is faster than anyone expected. Milky Way is not sitting still in space. It is plummeting through cosmos at 600,000 miles per hour. Roughly 850 times speed of sound. This velocity is not from expansion of space. From local gravitational effects. Specifically our galaxy being pulled away from local void toward denser structures beyond it. Local void distinct from but connected to larger KBC void. Exerts strong influence on our motion. Void itself is not pushing us. Rather, deficit of matter in void means less gravity pulling us toward it compared to gravity pulling us in other directions. Denser regions win tug of war, accelerating our galaxy away from underdensity. This speed is difficult to comprehend. 600,000 miles per hour means Milky Way travels about 167 miles every second. In single year, our galaxy moves about 5.2 billion miles through space relative to void. Even at this breakneck pace, void is so vast our motion barely makes dent. Would take hundreds of millions of years to cross from one side of void to other. Even at this speed. Meanwhile, void continues expanding due to cosmic expansion and dark energy. Growing faster than we can escape it. We are inside void now. Will remain inside it for foreseeable cosmic future. Local sheet adds another component to our motion. Local sheet is flattened structure of galaxies including Milky Way, Andromeda, other nearby galaxies. This sheet forms one wall of local void. Entire sheet rushing away from void center at about 260 km per second. Roughly 580,000 miles per hour. Our galaxy participates in this bulk motion along with neighbors. Sheet is not static. Actively being evacuated from void region. Flowing outward like water draining from depression. This motion ongoing for billions of years. Will continue for billions more. But there is more to our velocity than just escaping void. Milky Way also falling toward Virgo cluster. Rich concentration of galaxies about 60 million light-years away. Virgo cluster contains over 2,000 galaxies. Has enough mass to gravitationally attract everything in surrounding region including us. Adds another component to our peculiar velocity. Roughly 250 kilometers per second directed toward Virgo. Meanwhile Milky Way and Andromeda falling toward each other. Will collide in about 4 billion years. That motion adds yet another velocity component. When you add up all these gravitational influences, Milky Way's total peculiar velocity relative to cosmic microwave background rest frame is about 627 kilometers per second. That is velocity astronomers measure when they look at dipole pattern in cosmic microwave background temperature. These motions matter because they complicate cosmological measurements. When we observe distant galaxies and measure redshift, we need to correct for our own motion through space. Otherwise galaxies in direction we are moving appear blue-shifted. Galaxies in opposite direction appear red-shifted, creating false pattern mimicking cosmic structure. Astronomers known about these corrections for decades. Routinely apply them. But inside void corrections become more complicated because void itself creates large-scale bulk flows extending over hundreds of millions of light-years. Disentangling void effect from true cosmic expansion requires careful modeling of local velocity field. Our high speed through space is itself evidence for void. If we lived in typical region with average density, peculiar velocity would be much smaller. Maybe 1 or 200 kilometers per second at most. Fact that we are moving so fast indicates strong gravitational gradients in our vicinity. Exactly what you expect from being near large underdense region. Velocity consistent with void hypothesis. Would be difficult to explain without it. This makes our motion key piece of evidence in debate over whether KBC void exists and whether it affects measurements. Universe may be lying to us about expansion rate. But it cannot hide fact that we are racing through it at incredible speed. And this motion connects to deeper principle that void fundamentally violates. Cosmological principle is one of foundational assumptions of modern physics. KBC void threatens to shatter it. Principle states universe is homogeneous and isotropic on sufficiently large scales. Homogeneous means same everywhere. No location is special or different from any other when you average over large regions. Isotropic means same in all directions. Universe looks same no matter which way you look. These assumptions simplify mathematics of cosmology enormously. Allow scientists to model entire universe using relatively straightforward equations. Without cosmological principle, equations become vastly more complicated. Predictions become much harder to make. Principle has been remarkably successful, accurately describing many observations. But KBC void represents major violation of homogeneity. If void is 2 billion light-years across with 20% density deficit, that is huge in homogeneity. Even on cosmic scales, void is not small compared to observable universe. Represents significant fraction of volume within several billion light-years of Earth. More troubling, we happen to live near center of this abnormal structure. Seems to contradict idea that our location is unremarkable. Throughout history science progressively removed Earth from any special position. Copernicus showed Earth not center of solar system. Later observations showed solar system not center of galaxy. Galaxy not center of anything. Cosmological principle is ultimate expression of this trend. Not only is Earth not at center, but there is no center. Because every location is equivalent. Void challenges that worldview. If we live inside abnormally large underdense region, our location is unusual by definition. Voids are common in universe. But most are smaller than KBC void. Supervoids this large are rare. Finding ourselves in one raises questions about whether cosmological principle truly holds. Or whether it is only approximately true on scales much larger than previously thought. Some scientists calculate in universe governed by standard cosmology, void as large and deep as KBC void should be exceedingly rare. Perhaps 10 sigma statistical deviation. In typical random realization of universe's structure, you might not find one anywhere in observable cosmos. Yet we are in one. This suggests either we are incredibly lucky, or Standard Model is wrong about how structure forms. Defenders of cosmological principle argue void does not actually violate principle because homogeneity only applies at scales of several hundred megaparsecs or larger. Void is about 600 megaparsecs across, right at edge of where homogeneity supposed to kick in. Maybe universe is less smooth at those scales than assumed. Alternatively, maybe void is not as extreme as measurements suggest. Different observational techniques give somewhat different density contrasts for void. If true deficit is closer to 10 or 15% rather than 20%, statistical rarity becomes less severe. These counter-arguments preserve cosmological principle but require accepting measurements are less precise than thought. Another defense is we should not be surprised to find ourselves in unusual location because observers can only exist in certain types of environments. Weak anthropic argument. Perhaps intelligent life requires galaxies to form. Galaxies form preferentially in moderately dense regions rather than densest clusters or emptiest voids. If most observers live in mildly underdense regions, finding ourselves in slight void not surprising. But this argument only works if KBC void not as extreme as appears. 20% deficit is more than mild. Pushes boundary of what anthropic principle can explain away. Debate over cosmological principle not settled. Some researchers believe void is real and significant, requiring either modifications to cosmology or acceptance that Earth occupies genuinely unusual position. Others believe void is observational artifact, or not as extreme as initially reported. Still others propose principle holds on even larger scales. Apparent violation is temporary. Future observations should help resolve this. Surveys mapping universe to greater distances and depths will reveal whether large voids are as rare as standard models predict, or whether they are more common than expected. If big voids turn out frequent, cosmological principle survives but standard model needs revision. If they are truly rare, we need to explain why we happen to live in one. Origin of these voids reaches back to universe's first moments. Voids we observe today began as infinitesimal quantum ripples in first moments after Big Bang. During period called inflation, universe expanded exponentially for tiny fraction of second, perhaps 10 to negative 35 seconds. During this expansion, quantum fluctuations stretched from subatomic scales to cosmic scales. These fluctuations created slight variations in density of matter and energy. In some regions density was tiny bit higher than average. In others, tiny bit lower. Variations incredibly small. About 1 part in 100,000. But they were enough to set stage for everything that followed. After inflation ended, universe continued expanding but at much slower rate. Matter began clumping together under gravity. But gravitational pulling only amplified initial density differences. Regions that started slightly denser attracted more matter from surroundings, making them denser still. Created positive feedback loop. Denser region became, more strongly it pulled matter toward itself. Over millions of years these overdense regions collapsed into first stars, then galaxies, then clusters of galaxies. Meanwhile regions that started slightly less dense lost matter to denser neighbors. As matter drained away toward collapsing overdense regions, underdense regions became even emptier. These evolved into voids. Process is called gravitational instability. Turned barely perceptible initial ripples into dramatic large-scale structure we observe today. Cosmic microwave background radiation provides snapshot of these density variations when universe was only 380,000 years old. At that time variations were still tiny, visible only as slight temperature differences of about 100 millionths of a degree. But those temperature differences correspond directly to density differences. Warmer spots had slightly higher density. Cooler spots had slightly lower density. Satellites like Cosmic Background Explorer, Wilkinson Microwave Anisotropy Probe, and Planck spacecraft have mapped these temperature variations in exquisite detail across entire sky. Maps show mottled pattern of hot and cold spots at various angular scales. This pattern encodes seeds of structure formation. Scientists can take this pattern and run it forward in computer simulations to predict how structure should look billions of years later. Those simulations reliably produce cosmic web of filaments, clusters, voids that closely resembles what we observe. Match between predictions and observations is one of great successes of modern cosmology. Confirms understanding of how gravity shapes structure over cosmic time is largely correct. However, simulations rarely produce voids as large or as deep as KBC void. This is where tension arises. Initial quantum fluctuations were random, so every region had some chance of ending up as void or filament. But probability distributions matter. Small voids should be common. Medium voids should be less common. Extremely large voids should be very rare. KBC void appears to fall into extremely rare category. Raises questions about whether simulations missing something. One possibility is initial quantum fluctuations were not completely random but had subtle patterns that enhanced formation of large voids. Could happen if inflation did not smooth out structure as uniformly as standard models assume. Another possibility is gravity works slightly differently on large scales than general relativity predicts. Would change how voids form and evolve. Third option is universe simply has more variance in structure than cosmologists expected, making large voids less surprising. Each explanation requires further evidence. Observations of more distant voids in other parts of universe would help determine how rare KBC void truly is. If similar voids turn up frequently, suggests standard model underestimates structure variance. If they remain exceedingly rare, strengthens case for modified physics or unusual initial conditions. Quantum origin of voids is both elegant and unsettling. Means cosmic desert we inhabit traces back to subatomic processes occurring before atoms even existed. Randomness at smallest scales propagated upward to create structure at largest scales. Universe's organization is not designed or predetermined. It is consequence of random quantum fluctuations amplified by gravity over billions of years. This realization is one of profound insights of modern cosmology, but also means our location within this structure is result of chance. No reason we had to end up in void rather than filament. We are here because initial conditions in our region happened to be slightly underdense. That accident of quantum chance 14 billion years ago determines what we observe when we look out at cosmos today. Scale of these empty regions dwarfs human imagination. When you picture universe, you probably imagine sky full of stars and galaxies. But reality is opposite. Universe is overwhelmingly empty. Voids occupy roughly 90% of total volume of space. Galaxies and galaxy clusters crowd into remaining 10%, packed into filaments and walls surrounding voids. This is not just empty space in sense of vacuum between stars. It is empty in sense that entire regions hundreds of millions of light-years across contain almost no galaxies at all. If you could travel through void, you would fly for tens of millions of years at speed of light without encountering single galaxy. Isolation would be nearly absolute. This distribution creates lopsided universe. Most matter concentrates in small fraction of volume. Filaments are crowded with galaxies that interact, merge, evolve rapidly. Star formation vigorous. Black holes grow. Galaxies collide and trigger bursts of star creation. Meanwhile, voids are quiet. Few lonely dwarf galaxies drift through darkness, separated by vast distances. These void galaxies evolve slowly because they rarely interact with neighbors. They tend to be smaller, fainter, less evolved than galaxies in dense regions. Star formation sluggish. Many void galaxies contain large amounts of neutral hydrogen gas not yet condensed into stars. They are galactic backwaters, isolated from busy highways of cosmic web. Extreme emptiness of voids raises questions about how empty space can really be. Even in voids, dark matter is present. Dark matter makes up about 85% of all matter in universe, but does not interact with light, making it invisible to telescopes, detectable only through gravitational effect. In voids, dark matter much less concentrated than in filaments, but still exists at about 15% of cosmic average density. That might sound like lot, but spread over such huge volumes, amount of dark matter per cubic light-year is incredibly tiny. Additionally, voids contain dark energy, mysterious component driving cosmic acceleration. Dark energy appears uniform throughout space. So voids have just as much dark energy per volume as dense regions. In fact, because dark energy does not clump like matter, it becomes dominant component in voids where matter is scarce. Interplay between dark matter and dark energy determines void evolution. In early universe, matter dominated even in underdense regions. Gravity still mattered. As universe expanded and dark energy became more important, voids began accelerating their expansion. This acceleration makes voids grow faster over time, eating into surrounding filaments. Eventually, if dark energy continues to dominate, voids will consume more and more of universe. Filaments will thin out. Galaxy clusters become isolated islands in expanding ocean of emptiness. Billions of years in future, universe will be even emptier than now, with voids occupying even larger fraction of total volume. This future evolution is inevitable given what we understand about dark energy. Universe's destiny is to become increasingly hollow. Understanding void fraction of universe important for interpreting observations. When we measure average properties of universe such as overall matter density or expansion rate, we are averaging over both voids and filaments. If we do not account for fact that most space is void, might misinterpret what those averages mean. For instance, measurements of cosmic microwave background give average matter density of universe. About 30% of critical density needed to stop cosmic expansion. But that average includes both dense filaments and sparse voids. Local density varies dramatically depending on where you are. In filament, density might be 3 times average. In void, might be 15% of average. These variations matter when trying to understand local observations. 90% void fraction also affects searches for rare phenomena. For example, astronomers searching for distant supernovae or gamma-ray bursts most likely to find them in dense filaments where star formation is active. Finding these events in voids much rarer because voids contain fewer galaxies and less star formation. Creates observational selection effect. Most interesting astronomical events happen in busy 10% of universe. Not quiet 90%. We study universe from within active regions. Mostly ignore empty ones. But voids are just as much part of cosmic reality as filaments. Understanding them essential for understanding universe as whole. One void stands out as particularly impossible under current physics. KBC void defies probability in way that makes cosmologists deeply uncomfortable. Standard cosmology predicts structures form through gravitational collapse of initial density fluctuations. Larger and deeper a structure, rarer it should be. Small voids few tens of millions of light-years across are common because they arise from common small fluctuations. Large voids hundreds of millions of light-years across are less common because they require larger, rarer fluctuations. KBC void is 2 billion light-years across and 20% underdense. Computer simulations of structure formation using lambda cold dark matter model rarely produce anything this extreme. When researchers run thousands of simulated universes and look for voids as large and deep as KBC void, they find very few matches. Statistical likelihood of such void existing is extremely low. Some studies estimated improbability. One analysis calculated void of KBC's size and depth represents 10 sigma deviation from expected density. In statistics, 5 sigma result means less than 1 in million chance of being random. 10 sigma result is incomprehensibly unlikely. You would need to observe trillions of universe-sized volumes to expect to find even one such void. Yet here we are living in one. This is not small statistical anomaly. It is massive red flag suggesting something wrong with either observations or model. If observations are correct, which multiple independent studies suggest they are, then model must be missing something. One possibility is initial density fluctuations after Big Bang were not as smooth as standard inflation models predict. If inflation produced more power on large scales than expected, large voids would form more easily. Would require modifying understanding of inflation. Already speculative part of cosmology with limited direct evidence. Another possibility is structure formation proceeded faster or differently than standard models predict. If gravity was effectively stronger in past, or if dark matter behaves differently than assumed, structure would form more vigorously, creating larger voids and richer clusters. Some researchers propose modified gravity theories where strength of gravity varies with scale or environment. These theories can enhance structure formation. Make large voids more likely. Third option is KBC void not as extreme as measurements suggest. Perhaps observational biases or systematic errors in galaxy surveys made void appear deeper and larger than really is. Different groups using different datasets measured void's properties, found somewhat different results. Some studies find 20% density deficit. Others find closer to 10 or 15%. If true deficit is on lower end, statistical rarity becomes less severe, though remains challenge for standard models. Confirming void's exact properties requires more data, particularly deeper galaxy surveys that can map void's extent and density profile with higher precision. Future missions like Euclid Space Telescope and Vera Rubin Observatory will provide much better data. Existence of KBC void has become ammunition in debates about standard cosmological model. Critics of lambda cold dark matter point to void as evidence model fails on large scales. They argue structure formation not well understood. Standard model makes incorrect predictions. Defenders of model counter that rare events sometimes happen. Finding ourselves in statistical outlier not impossible, just unlikely. They also note other aspects of cosmology such as cosmic microwave background match lambda cold dark matter predictions very well. Abandoning or significantly modifying model based on one anomalous structure seems premature. Nevertheless, void cannot be dismissed. Real observation that requires explanation. Either we accept we happen to live in exceptionally rare location, which violates spirit of cosmological principle, or we modify models to make large voids more common, which requires changing fundamental assumptions about inflation, dark matter, or gravity. Neither option is satisfying. Both represent major shifts in how we think about universe. KBC void has become focal point for cosmological debates, precisely because it sits at intersection of observation and theory, challenging most basic assumptions about how universe works. Until this tension resolved, void remains cosmic puzzle refusing to fit neatly into current understanding. These vast emptiness regions serve unexpected scientific purpose. Cosmic voids are best places in universe to study dark energy, because voids are only regions where dark energy dominates completely. In dense areas like galaxy clusters, gravity is strong enough to resist cosmic expansion. Clusters hold themselves together gravitationally despite universe expanding around them. Even on slightly larger scales in filaments, gravity is still relevant, slowing expansion of space in those regions. But in voids where matter sparse, gravity becomes negligible. With no significant gravitational pull to counteract it, dark energy controls what happens. Voids expand faster than cosmic average, driven by dark energy's repulsive pressure. This makes voids natural laboratories for measuring dark energy strength and properties. Dark energy is one of most mysterious components of universe. Discovered in 1998 through observations of distant supernovae, dark energy accounts for about 68% of universe's total energy. Behaves opposite to normal matter and gravity. Where gravity pulls things together, dark energy pushes space apart, accelerating cosmic expansion. Exact nature of dark energy remains unknown. Could be cosmological constant, unchanging energy density built into fabric of space itself, or could be dynamic field varying in strength over time and space. Distinguishing between these possibilities requires precise measurements of how expansion accelerates in different environments and at different times in cosmic history. Voids provide cleaner signal for these measurements than dense regions. In dense areas, gravity complicates everything. Local gravitational pull from nearby masses affects galaxy motions, making it hard to separate cosmic expansion from local effects. In voids, those complications minimal. Galaxies move almost entirely due to cosmic expansion and dark energy. By measuring how fast voids expand compared to predictions, scientists can test whether dark energy behaves as constant or whether it changes. If dark energy stronger in voids than elsewhere, or if it was different in past, would show up as deviations from expected void expansion rates. Another way voids help is through their shape. Dark energy affects not just how fast universe expands but also how it expands in different directions. If dark energy truly uniform, voids should expand equally in all directions, staying spherical. But if dark energy has variations or if there are other unknown forces, voids might expand more in some directions than others, becoming elongated or distorted. Observations of void shapes can therefore reveal whether dark energy is uniform or has structure. Current measurements show most large voids roughly spherical. Supports idea that dark energy is uniform, but measurements not yet precise enough to rule out small variations. Improved surveys in coming years will provide much better shape measurements. Expansion history of voids also encodes information about dark energy. Voids have been growing for billions of years. Current size reflects entire history. By modeling how voids should grow over time given different dark energy properties, scientists can compare predictions to observations. Constrain what dark energy must be like. For example, if dark energy was weaker in past and became stronger recently, voids would have grown slowly at first then accelerated. If dark energy been constant, voids should grow at steady accelerating pace determined by that constant value. Observations of voids at different distances, which means different times in past, allow testing these scenarios. One particularly useful technique involves measuring void edges. Boundary between void and surrounding filament is transition zone where density rises sharply. This boundary evolves over time as matter drains out of void and accumulates in filaments. Sharpness and location of this edge depends on how fast void is expanding, which depends on dark energy. By mapping void edges at different cosmic times and comparing them to simulations, researchers can infer how dark energy influenced void growth. Early results suggest dark energy has been roughly constant over past several billion years, consistent with simplest models. But ongoing studies refining these results, looking for any deviations that might hint at more complex behavior. Studying dark energy through voids is active area of research. Future surveys will discover and characterize thousands of voids at various distances and sizes. Each void provides independent measurement of dark energy's effects. Combining many measurements will dramatically improve understanding. If voids reveal dark energy is changing or has structure, would revolutionize cosmology. Even confirming dark energy is constant and uniform would be important. Would rule out many alternative theories. Either way, voids proving essential tools for probing one of universe's deepest mysteries. KBC void being largest and closest supervoid offers best opportunity for detailed study. Its proximity allows measurements impossible for distant voids. We are inside cosmic hole 2 billion light-years wide. This is not metaphor or speculation. This is observation. KBC void is real. Its effects measurable. Its existence challenges fundamental assumptions about cosmology. Whether it explains Hubble tension. Whether it requires modified gravity. Whether it makes us unusually positioned in universe. These questions remain open. But one thing is certain. Universe is far stranger than we imagined. And our place within it is more unusual than we ever suspected. We are cosmic castaways. Drifting through desert of space. Measuring universe that may not be what it seems. Every observation filtered through lens of our abnormal location. Every conclusion potentially biased by emptiness surrounding us. NASA confirmed this in buried technical papers. 3 astronomers discovered it in 2013. And most people still have no idea. Because accepting this truth means accepting we occupy special location. Unusual position. Not representative of cosmos as whole. Everything science spent 5 centuries trying to avoid. But evidence keeps mounting. Void exists. Our measurements discrepant. Physics behaving differently here than predictions suggest it should. We live inside cosmic anomaly. Statistical impossibility. Structure so rare simulations struggle to produce it. Yet here we are. Conscious observers developing technology to study universe from inside one of its most extreme features. Question is not whether void is real. Question is what it means for everything we think we know. If local measurements do not represent universal truth. If expansion rate varies by location. If age of universe depends on where you measure it. Then cosmology needs revolution. Not small adjustment. Complete rethinking of how we interpret observations. Or maybe universe is exactly as models predict. And we just got incredibly unlucky. Ended up in rare location that distorts everything we measure. Cosmic coincidence. 1 in trillion chance. Either explanation is unsettling. Either our models are wrong. or we are special. Both options violate principles science holds dear. But evidence does not care about principles. It simply is. And evidence says we are inside void. Hole in fabric of cosmic structure. Emptiness that extends farther than light can travel in 2 billion years. Next time you look up at night sky, remember this. That darkness between stars is not just absence of light. It is fundamental property of region we inhabit. Void is not backdrop. It is environment. Shaping observations. Influencing measurements. Determining what we can know about reality beyond our cosmic bubble. We thought we understood universe. Turns out we were measuring from inside funhouse mirror. Distorted. Warped. Not representative of cosmos at large. NASA admitted it. Scientists confirmed it. Mathematics demands it. We are not in universe we think we are. We are inside something stranger. Something that should not exist according to laws we believe govern reality. Yet it does exist. We live within it. And every observation we have ever made about cosmos filtered through its impossible geometry. That is truth they buried in technical papers. Truth most people will never read. Truth that changes everything about how we understand our place in existence. Universe is hollow. We inhabit the hollows. And measurements we make from here may never tell us what reality looks like beyond these walls of emptiness. This is our cosmic address. Not just Milky Way galaxy. Not just local group. Not just Laniakea supercluster. But inside KBC void. Hole in space 2 billion light-years wide. Statistical anomaly. Impossible structure. Place that should not contain conscious observers yet somehow does. We are here. We are measuring. We are discovering reality is stranger than anyone imagined. And universe, for all its vastness and majesty, is lying to us about what it truly is.